All right, welcome in Calc 3. It's Tuesday, November 16th, and we are the start of week 14, right? Almost to Thanksgiving. We have one more video after this one this week, and then we have one video next week, and then it's Thanksgiving, and then we just have one more week of class left after that. So we are getting close to wrapping this all up, which makes sense because we are in 14.6 today, talking about triple integration. We've talked about double integration, and now we want to go up in one more level in complexity here. And there is such a thing as quadruple integration and quintuple integration. We don't go that far in this class, but the idea would be similar, and we could just keep raising that level. Now, what does that tell us? Let's do a little recap of some of the applications that we've been talking about and how single integrals and double integrals and then eventually triple integrals fit into all of that. Yeah. So before we even start 14.6, let's take a look and sort of recap what we got going on here. So, for instance, what if I say here that the function is the constant 1? Okay. And I asked you for what this would mean. If I said I want the single integral from a to b of dx, right, where the function here is 1. This would provide, this would actually just be b minus a, which is the length of the interval from a to b, right? That's all that is, the length of a to b, right? If I do a double integral over a region, dA, that's the next thing up. This is the area of R, that region, right? So integrating over 1 dx, single, gave me a length. Integrating over 1 dA, double integral over that, gave me an area. So I bet you could probably guess, if I were to do a triple integral, you might even be able to guess what letter I would use here, right? Length was x, area was a. That next dimension concept up would be volume, right? And so I could think of this as triple integrating over something called dV, where over some three-dimensional solid, maybe call it T, that would be the volume of capital T. So you see there's a one-dimensional idea, two-dimensional idea, three-dimensional idea, right? Now, if f is any integrable function, we can sort of go through the same sort of idea. And here we could say that the integral from a to b of f of x dx, that could be thought of as the area under the curve, or even net area, if you wanted to be a little bit more precise, under curve. Right? And that's what you spent a lot of time in Calc 1 doing, right? The double integral over r of f of xy dA, that gets us the volume under the surface f, right? So where would that take us with the triple integral? Over t, f of x, y, z dv. Well, here we start to have some issues, right? Because what's the next dimension up from volume? Well, this is some four-dimensional idea, right? This is area, which is two-dimensional, volume, which is three, and then this would end up just by pattern. What would that be? Like the amount of four-dimensional space under, whatever under means, in 4 dimensions, f of x, y, z. We start to lose this application, don't we? This doesn't really move on in that way. Now, triple integration is useful in here, right? The analogy continues, right? But here it seems like we have, right, equals maybe 4-dimensional space, question mark, hypervolume, some say. I would argue that hypervolume doesn't tell me anything more about it, right? If you say, oh, it's gobbledygook, great. I don't know what that is. If you say, oh, it's hypervolume, I still don't really have a good idea what that is, right? I don't think I've ever seen a hypervolume, right? So this sort of is no longer the path here, right? This seems to be like a dead end as far as applications, right? However, this is not a dead end. We could think of it in a different way. We have another application that you might have looked into, and that was the mass of certain objects, right? So suppose we had, some density function, right? We could have a density function like that, and I could ask, well, what is the interval from a to b of a density function with respect to x dx? That ended up being the total mass of a one-dimensional wire, right? Whose the wire sits on the x-axis, and it starts at A and it ends at B, right? And so we have a length of a length of wire, and we know the mass density at each point, rho of x, right? And we can integrate over that mass density all the way from A to B to accumulate the total mass of the wire. Nice. Well, if I did a double integral, and we just did this the other day, right? We end up getting the mass of a lamina. Right? So as long as this is a density function, a mass density function, and I double integrate over that density function with respect to A over R, I get the mass of a two-dimensional lamina. That's a thin plate, right? That's the shape of R. Well, I think I have a natural extension in this way, right? If I went to triple integrals, I wonder if you could sort of guess what this would end up being. Right? Any takers in chat what this would be, you think? I mean, we had mass of a one-dimensional wire, mass of a two-dimensional lamina, and now mass of a 3D. Yeah, exactly. I wouldn't call it a lamina anymore because lamina is reserved for two-dimensional space, but perfect, right on. Let's call it something else. We're going to call it the mass of a 3D just solid. How about that? A solid. Yeah. So suppose I have a three-dimensional object, right? Some like this, right? Three-dimensional object, yeah. And I could tell you the density at each point. I could measure that somehow. And what this is saying is that I could get the total mass of this object by triple integrating over its density function. That seems pretty good, right? I'm able to now think of the mass problem in terms of integration. Yeah. And so there is a nice little way of thinking about that. So triple integration has its place when you're working with some density function. Now, what's fun about this is that this doesn't have to be density of just mass. This could be blank density, and the integral will add up to get the total. So if this was like charge density function, right? Then you could triple integrate over the charge density to get the total charge. If this was even a population density, right? Suppose I know about Winnebago County, right? And I know sort of the population dynamics of Winnebago County, and I happen to know the density of population. Well, what I could do then is integrate over the region. This would be a double integral because Winnebago County could be thought of as a two-dimensional region, right? Where I would then integrate over the population density to get the total population, right? And so that's a really nice way of thinking about integration. That's what it does. It takes density functions, things that you know something about at each point, sort of, per measured unit here. So here it's per, length unit, here it's per area unit, and here it's per volume unit. But then I can now sort of add that up if I can understand at least the dimensions, the geometry of the object itself. That would be the important consideration there. Yeah? Awesome. So that is sort of a recap and getting into the triple integral. So hopefully this makes a lot of sense. This puts all of these sort of integrals that we've been learning into perspective, yeah? And all the different sorts of things that we can calculate and even keeping track of what the dimension is, yeah? Awesome. Okay. Now, let's get now into calculating triple integrals. What does that look like? How can we work with them? So to get us started, I am going to just let's practice doing an iterated integral that has a certain form. So let's go ahead and I'll just do an example. We'll start this out, 14.6, triple integrals. To calculate a triple integral, we are going to be able to relate this to a iterated integral of 3 integrals, right? Just like we did with double integrals, we were able to connect it to an integral of an integral, right? Here we're going to do an integral of an integral of an integral, right? And so we'll be able to at least unpack a triple integral in that way. So to get us started with that, let's just say we want to calculate the following. Let's say I want to do the integral from 1 to 2 of the integral from 0 to 3 of the integral from -1 to 1 of x squared y plus y z squared, and we have dx, dy, dz. Okay, so let's focus on just being able to calculate this. Then we'll talk about triple integration in and of itself and how we might set up a triple integral and then calculate it using a calculation very much like this. But here, this is just concentrate on at least the calculation part. At the end of this will be a value, and hopefully we could put some meaning to that value at the end of the calculation. Right? But here we just approach this like we've been doing. I'm going to integrate the inside first with respect to x. These are x values. So I want to integrate this with respect to x from -1 to 1. So when I do the next step, these are literally just like parentheses for now. I don't pay much attention to these. And I'm going to integrate this now with respect to x, meaning all other variables are treated like constants. So this is going to be x cubed over 3, but x cubed times the y over 3, plus this is a constant, so the integral of a constant is just x times that constant, evaluated from -1 to 1, dy, dz. And all you have to remember is that these are x values, so I'm replacing x with these limits here. So I'm going to go ahead and do that on this next step. I plug in a 1, I'm going to get y over 3, 1/3 y. I'm going to plug in the 1 here. I get plus yz squared. Now I subtract, plug in -1 here. So this is going to be minus a minus 1/3. So that's going to be plus y over 3. And then minus, plug in the -1. So minus a minus, so plus yz squared. Evaluate dy dz. And go ahead and simplify before going on, but now I'm right back to double integral territory, aren't I? Looks like I get 2/3 of these, so I'm going to say 2/3 y, and I get 2 of those, plus 2yz squared, dy dz. Yeah, that's all there is to it. Now I'm just going to continue on my way here. So now next step is integrate with respect to y. So that's going to be y squared divide by 2. The 2's will cancel, and I still have the 1/3. Here, the y squared, so y squared divide by 2, so the 2's cancel. I have the z squared, that's plus, evaluated from 0 to 3, dz. All right. Go ahead and plug in 3 for y. So this is going to be the integral from 1 to 2. Plug in the 3, I get 9. 9 divided by 3 is 3, so that's going to be 3. Plus 3 squared, which is 9, z squared. Minus, plug in 0, plug in 0. So I'm down to that. And now one more integration, and we should be good. This is going to be 3z. This is z cubed over 3. So 9 divided by 3 is 3. Evaluated from 1 to 2. Let's see what I get here. I plug in 2 here. I'm going to get 6 plus 2 cubed is 8. 8 plus 10 times 3 is 24. Minus plug in 1, so 3. Minus plug in 1, so minus 3. And it looks like at the end of the day I get 24. Nice. Okay. So steady goes it, right? That's all it is, right? You just, you're going to have to integrate just the first one, finish it, do the second one, finish it, simplify, do the third one, finish it. Yeah? Now, just like in double integration, when you do a double iterated integral like this, a triple one, since I'm integrating with respect to x first here, these could be functions of two variables. Yeah, because y and z are considered constants relative to x. So the full story of this could be something like this. I could integrate from some a to b of some integral from some f1 of z to f2 of z of the integral of from some, let's say, g1 of y and z to g2 of y and z, and then we have w of x, y, z, dx, dy, dz, right? That would be the full brunt of it. That's the full story, right? So you can have a function of three variables here. If you're integrating with respect to x first, that means these can be functions of y and z. Then you're integrating with respect to y, so these can only be functions of z. And then finally, when you get to z, these have to be constants because now it's a single integral. And yeah, fundamental theorem allows only constants there, right? So just like the limits got more complex, right? You could have functions in double integrals like this. Triple, well, now we have functions of two variables that could literally sit there, yeah? So that can be a little bit more complicated, right? But the calculation itself is still handled the same way. So let's get into now a little conceptual here. And I want to also show pictures. Now, I like the old textbook that we used to use. So I'm going to show you pictures from the old textbook. I do not actually like the presentation of the new textbook, the Larson book, our current book. I do not like its presentation. I think it's rather missing lots of stuff. But they don't miss on the homework. They still ask you all the questions that the old book did, but I don't think they do nearly a good job of showing you the pictures and showing the different cases. So I'm going to actually resort to the old book to show you graphics and some pages and some pictures here of what's going on and how to set these triple integrals up. So hopefully you find that more helpful, right? Okay. So we will want to make sense of what this means. The triple integral over now a three-dimensional solid. So the domain of integration is already a three-dimensional object, right? Just like in Calc 1, where the single integral was an interval, the domain of integration was an interval from A to B. Like double integration, the region of integration was a two-dimensional region, right? Some sort of shape in the xy plane. Here, in triple integral, the domain of integration itself is already three-dimensional. So it usually will have a top surface and a bottom surface. It'll usually have a left surface and a right surface. I don't know if that's mirrored for you, but anyway. And it'll have a front surface and a back surface, right? So it'll usually have 6 surfaces to sort of describe what that object is, that three-dimensional object. And just like single integration and double integration, you have to find some way to sort of go through every point along the way, right? In Calc 1, we went from A to B and we didn't think much of it because we just started here and we traversed like that. And that's the way that we went through the one-dimensional domain of integration, right? In 2 dimensions, right, in double integration, we did have to think a little bit about it, right? If we had something like this, right, being our region here, we had a couple options, right? We could do arrows that work this way, from bottom function to top function, and then sweep these arrows through like that. Or we could think from left function to right function, and then sweep the arrows from low to high. Or we had a radial option. We had the polar option, didn't we? We could do radial arrows from that, and then move theta from here to there, right? So we had actually 3 options to traverse the 2-dimensional domain of integration. Well, I have news for you folks. In a 3-dimensional domain, let's just draw a box for now. Well, now I have all sorts of ways to travel to make sure I hit every location in this 3-dimensional object, right? I might choose something to go from bottom surface to top surface, right? That might be a good first move, saying that, okay, let's think about going from starting at the bottom surface and going up vertical arrows until I hit the top surface. That would be one way to start. We would call that a DZ start, right? Because of the vertical arrows. I could think of starting from the back wall to the front wall. Hopefully that perspective is working a little bit for you there, right? That would be a first move for arrows. I could say, okay, think of this as a back wall. Think of this as some back surface. Think of this as some front surface. And I want to start off by going from back to front. That's an option. The third option would be to start from the left wall and then go out until the right wall. Those are all 3 very legit choices to start traversing through this whole thing. So the idea that we do is we pick one of these, and then we will project the 3D surface onto the plane of the other 2 variables. For instance, if I choose vertical arrows first, that's a DZ first integration. If I pick Z first, that means I will project it into the XY plane, the one that doesn't have Z. So now I need to look at that box from a top view. From there, it looks like a 2-dimensional object, and from there, it's a double integral. So yes, triple integrals are like double integrals with just one extra layer, right? With just one extra layer, okay? So let's see what we can say conceptually here. This is the generic triple integral over some f of x, y, z with respect to v. What we will learn very quickly is that dv actually has many ways to be unpacked. It could be unpacked as dz, dy, dx. It could be unpacked as dz, dx, dy. That's a different order. It could be dy, dx, dz. It could be dy, dz, dx. Could also be dx, dy, dz. And finally, dx, dz, dy. Right? There are 6 combinations of those 3 differentials. And so there's lots of different ways to unpack a dv. So the complication, it does complicate, right? Going up the next level has certainly added a layer of more complication. That is for sure, right? Because remember, with 2 differentials, we really only had the 2 ways to put them, right? dx, dy, dy, dx. That was it. But with 3 differentials, there's now 6 combinations that we can have, right? Okay, so let's unpack these slowly. Like I said, usually you pick a first one. Do you notice how like this first one is dz? And then you pick dx, dy or dy, dx. Do you see that? That's how we usually think of it. So we usually pick, which one do we want to do first? Once you pick that, then you look in the plane of the other 2 variables, in this case the xy plane, in this case the xz plane, and in this case the yz plane, and then it becomes a second integral or a double integral in that plane. Okay? All right, maybe it's time to look at a picture. Let's take a look here. Yeah, so take a look here. This is what it would look like to do dz first. Okay? So again, what you're looking at here, this capital T, is a three-dimensional solid. This is not the surface that you're integrating over. This is the solid that is your region of integration, your solid of integration, if you will. All right? F of x, y, z is not pictured on this graph. Right? We're only picturing the domain, which is three-dimensional already. Now notice that this is such a way that the bottom surface actually can be described, and they've called it K1 of xy. So that bottom surface has a description. Great. This top surface has a description, K2 of xy. Awesome. This makes this a really good choice to be dz first, because we can go from bottom to top. See that? Arrows will always start going through the bottom surface. They start there, and they always exit going vertically up through the top surface, no matter where that arrow is. If it's over here on this corner like this, no matter if it's on this edge over here or in the center over here, right? It'll always start from the bottom surface and go up to the top surface. That's what we call the dz integral first, right? Awesome. Then the second step after that will be to think of what does this look like in the top view. You're going to project that into the xy plane. That creates a region R. Now, hopefully in that region, we can understand that this is a function and that's a function. And so now I might choose to do dy dx, going from this function to this function, and then pushing the arrows from left to right. Right? So there's often going to be two pictures in play here. They've combined the two pictures into one. They've done the 3D domain. You'll see me do sort of a rudimentary rough picture of that. And then I'll draw a second picture that shows the XY plane in our standard way, right? This is showing both of those in the same picture, so it looks a little maybe different than what you're used to. But this is still just the XY plane down here, right? And that's the R that we would then double integrate over by that. Okay, let's see here. I would like to now do an example, okay? Let's try our first example here. And please in chat, let me know if there's any questions as we go. All right. They want us to evaluate this triple integral over t z dv. Okay. Then they describe what t looks like, where t is the solid in the first octant. Okay, that means everything's positive, x, y, and z. And it's bounded by the graphs z equals 1 minus x squared and y equals x. Okay? Now, I'd like to do this problem without GeoGebra at first, right? Just to get a sense of how I can do this on paper, right? Obviously, you might want some help with the graphing and the visualization, right? And so I'm not opposed to that. We'll do that in a little bit. But I think our first attempt at this, let's see if we can at least get a rough picture down, right? From just this description, right? Awesome. So let's try this. What can we do here? So let's go ahead, and I want to graph what t looks like. Okay, so there's my x-axis. Here's the y-axis. There's the z-axis. Okay. Now, first things first, we have z equals 1 minus x squared. That's actually a cylinder because it's missing the y. Remember, we talked about that way ago in the semester. This is missing a y. That's actually good news for graphing, because what this will look like is in the xz plane, which is this left wall, this will look like an upside down parabola, right? It's going to look like 1 minus x squared. And it's going to have that same shape to the left and right for all y values. So the orientation of this is going to be a parabolic bowl upside down and going that way, right? So let me get a picture down here. When x is 0, z is 1. So let's go ahead and I'll put z to be 1 there. And when z is 0, it looks like x will be plus or minus 1. Remember that this is the first octant, so there's nothing behind the yz plane. So there's nothing behind there. But it does hit x equals 1, which is here. And so this is that parabolic shape, like that. Okay? Now, with that parabolic shape there, remember, we're going to get the same exact shape whether the y is 1 or 2 or 3 or 4. We're going to get that same exact shape. So one way we can do this is make sure I draw a parallel line here. Let's see. This is where my art skills are going to really suffer here. This is not great, but we'll try. Try to be as parallel as possible, because that's the best way to trick your brain into thinking there's 3D happening on the paper. Right? All right, what do you make of that? Would you agree with that? This is z equals 1 minus x squared. That's at least the surface, that parabolic cylinder right there. So it looks like a bread container, right? You open that up and put the bread in, right? Something like that. Okay? So that takes care of this. But we have not utilized y equals x. Now, y equals x, of course, is a straight line in the xy plane. Notice that there's no z value here. So it's going to look like a straight line in the xy plane, and it's going to look like a straight line for all z values. In other words, this is going to be a vertical plane. This is going to be a vertical plane, yeah? And so y equals x is 1, 1. That goes through 1, 1. So I get this sort of shape here. This is what it looks like on the floor, right, like that, right? And now here's the fun part. This is where it takes some visualization skills. What would happen if I took a piece of bread or a loaf of bread that looked like this, and I cut it vertically at this angle, at this bias like that? Just cut it like that. What would that look like? Right? Well, I think it would look something like this. See that? Now, what's my solid? It's only this piece here. This is all extra drawn, right? Because T is the solid in the first octant, bounded by the graph, this, and this plane. So I get none of this over here. This is just extra so to visualize. So this ends up being our 3D object that we are integrating over. This is the solid of integration, right? Like that, okay? Awesome. Now that we have a good feeling on what that looks like, okay, now we have to make a decision. How do I unpack the dV? Okay, now I'm sort of got the idea of the visualization that's going on here. Now I have to make the decision on how to unpack dV. So I'm going to put this over here. And the things you're looking for here are going to be, do you understand how the bottom surface is and the top surface is? Or do you understand the left surface and the right surface? Or do you understand the back surface and the front surface? Right? So those are the questions that you sort of have to ask yourself. It's like, what is the appropriate first step here, right? Well, to sort of go with our previous example of doing a DZ first, let's see if we can think of this as from bottom surface, arrows starting from the bottom of the shape, going vertically until it hits the top surface, right? So I'm going to use vertical arrows first here. Now let's think about this. What would be a description of the bottom of this surface? What is the description of this surface? Well, that is z equals 0. It always starts on the floor, doesn't it? All arrows would start on the floor and then go up until it hits that parabolic top, right? That parabolic top is like this, and it always starts at the bottom, and it always goes straight up until it hits. Sometimes, you know, it has to go quite a ways, quite a distance z to hit the top. Other times it's real short. It hits it right away, right? But I can say generally that this starts from the bottom, which is z equals 0, and it goes up until it hits the parabola, the parabolic cylinder, which is z equals 1 minus x squared. This allows me to unpack this the first way. What I can say here is I have the integral of the integral z dz, and I'm going to hold off on the other two for now. At least I can get the dz done correctly here. Z starts at 0 and goes to the top surface, which is 1 minus x squared. Everyone with me there at least? In chat, confirm if you're with me. Type something in chat. I want to make sure that you guys are there. So let me know. We have at least set up the dz part. Okay, good. Good. All right. Now we're down to a double integral, right? This means I desperately now need a picture in the xy plane. So I need to think now, what does this look like top view? What does this look like if I just projected this downward into the xy plane and flattened it, right? So a second picture, I usually draw a second picture to do this. And I highly encourage you to do the same. So now I have to think about, what does this look like in the xy plane? Well, that's going to look rather triangular, isn't it? I'm not going to see any of this curvature from looking above, right? In fact, all I'm going to see is really this like that and like that, right? Here's x equals 1. Here's y equals 1, like that. And this line here, right there, is this line there, isn't it? So now I do double integral things, right? So now I can choose dy dx by using vertical arrows, or I can choose dx dy by doing horizontal arrows. I'm going to choose vertical here. So I'm going to go from bottom line, bottom curve, to top curve. All right, let's think that through. So I'm choosing to do a dy dx. Okay. Y starts at the horizontal line, y equals 0. And the arrow goes up until it hits this diagonal line. Well, why is this a diagonal line? It's a diagonal line because it's on this plane. What is this plane? This plane is y equals x. So this starts at y equals 0 and goes up to y equals x, that diagonal line. Then, where do the vertical arrows get pushed from left to right? They start at 0, and they get pushed until they get to 1. And there you have it, folks. That's the setup of our first triple integral. It's a little intense, isn't it? It's a little intense. But just as with all things, with a little practice, you can set these up pretty decently. Okay. Nice. And for time purposes, I think I won't necessarily do the actually do this. We'll stop at setup only for this one, because I'd rather, I think, use our time to do something else, right? To sort of say, this isn't the only option that we have. we could have set this up in a different way, and I'd like to show you that. Not that it's a better way, I just want to show you a different way, right? I pretty much think this is probably the easiest of all of the 6 setups that could happen, right? But I do want to show you an example of setting it up in a different way, maybe dy first, right? So we can see what that looks like, okay? So I can say or, so this is a perfectly good setup. So if it's just said setup using some order, you're done right there, right? That's the finish of a setup only, right? I'm saying that because I think in your test, you might have some setup onlys, right? And so that's what I'm looking for when it says setup only. You have to unpack the DV in some way and then set up the appropriate limits. And then you would stop after that. Now, let's talk a little bit about dy first integration. I think I have a picture for you here. Yeah. Okay, let's try this next picture here. This is not a picture of this example, but I am going to apply what I'm showing you to this example after I show you the first problem here, the first picture. All right, take a look at this here, right? So we have this 3-dimensional solid as our domain of integration right here. And this is such that it looks like I can tell what the left surface is and what the right surface is. In fact, they've described these are sort of left and right surfaces as a function of xz and a function of xz. Do you see that? So if I do a dy integration first, I'm thinking of arrows going from the left surface to the right surface. Once I do that and have that description of left to right, then I need to look from this way over here and project back onto the xz plane and see what it looks like there. That will then be a 2-dimensional surface, right? Sorry, a 2-dimensional region, right? In the xz plane. And that would be the picture I would need to draw to finish the double integral, right? So doing a dy integration is going to go from left surface to right surface. That's the key idea. Let's apply that to this same picture. I have a really good picture here, so I don't want to draw another one, right? So I want to get double duty out of this problem here. So imagine I did not draw this vertical arrow, and now I want to think about this from going from left surface to the right surface. Think about how arrows work. Think about, like, you know, I don't know if you can think of like a field of arrows, like radiating through, right? They would always enter this left wall, right? Enter this left wall right there, right? And they would exit this diagonal wall right here. You see that? That's how it would always start on the left and exit the right. That's what you have to pay attention to when you're setting up these triple integrals. So here we go. I'm integrating z, and I'm choosing now to set this up with dy first. So now I have to think about what is left surface and what is right surface. The left surface is pretty easy. This is the xy, this is in the xz plane, which means that y equals 0. So this always starts at a y equals 0, and it goes until it hits this diagonal plane. But what's the diagonal plane? It's y equals x. So my first integration here goes from y equals 0 to y equals x. See that? Not bad. Now, though, I do have to draw a second picture. What does this look like in the xz plane? What does this look like when I look at it from this way? When I look at it from this way, what would I see? Well, do you notice that all I would see would be this shadow? I would see the parabolic surface shadow there. Right? I wouldn't see this sort of coming out at me at an angle. I would just literally see the outline of this parabolic shape. Right? So in other words, this would look like this parabola like that. And in fact, this would be z equals 1 minus x squared. Right? Because this is what it looks like in the xz plane. Right? So now from here, I can choose, do I do a dx dz or a dz dx? Well, if I did vertical arrows from here, this would be a dz dx. And now I would think z starts at what? Well, this is z equals 0 until it gets to z equals what? 1 minus x squared. And then x gets pushed from 0 to 1. That's an alternative setup. And it demonstrates the use of dy first. Either one of these are acceptable setups. All right, with that being said, how are we doing? Okay. Let's try a new picture. Let's try a different one. Okay. You're understanding. Good. I enjoy that. That's great. Okay. All right, let's try this. They want us to evaluate the triple integral over t of the square root of x squared plus z squared dv. Okay. And they tell me that t is the cylinder, is the region bounded by, solid, bounded by the cylinder x squared plus z squared equals 1, and the planes y plus z equals 2 and y equals 0. Ooh, okay. Well, that sounds fun. Okay. So again, I'd like to try this without GeoGebra just to see if I can get this on paper. Because some of these you can just sort of figure out on paper, and I would encourage you to do that at first. I know it's hard, I know it's difficult, but that's good for you, like vegetables. But with that being said, obviously there's problems in the homework that might be a little too much to visualize and say, I can't tell what this is at all. And you might have to type that into GeoGebra. Now, I hesitate because GeoGebra does not do intersecting surfaces very well. And I'll show you an example coming up here where I had to spend like 30 minutes drawing the thing in GeoGebra. So I don't know if that's helpful, right? I mean, if you have to spend 30 minutes drawing it on GeoGebra, I probably could have done something by hand in that time. But anyway, so that's my point is you might want to do some of these simpler ones, and I'm not saying that they're easy. I'm not saying that they're simple, but some of these you can sort of get a feeling for just by understanding that, this is a cylinder, these are planes, and just plugging in some values and getting that picture going on. Okay. All right, so let's try that. See what we can say. So here's my 3D picture. Let's try it. Okay. Let's get a hold of this cylinder. Now, this is a cylinder because it's missing y. So this is going to look like a circle of radius 1 in the xz plane, but it's going to look like that circle for all y values, isn't it? Okay. So that's going to get me something that looks like, so here, let's say that this 1 unit, this is 1 unit, this is down here below 1 unit, like that. And so maybe it does something like this. We can go behind here 1 unit. Something like that. My perspective kind of sucks, but that's all right. But now, right, this is like a tube because it's got this circle that lives in the XZ plane. It lives on this left wall. It's going to look like that circle all the way through, right? So again, I'm going to need a nice ruler here to get nice parallel lines, as best I can anyway, to sort of get the feeling of that cylinder, right? Right, something like that. That's not terrible. It's not great, but it's not terrible either, right? Okay. So that's my cylinder. X squared plus z squared equals 1. Now I need to get the planes. Okay, well, y equals 0. That's a nice plane. That is the left wall. So I should have assumed that I was going to have to draw it this way as well. But y equals 0 is this left wall, so there's nothing to the left of this. So it was appropriate to just draw the cylinder to the right. Okay. Now let's get to this. Notice that there's an x missing. So if I can graph this in the YZ plane, which is this back wall, right, which is this YZ plane is right here, right, then I can theoretically just make that all x, make that same shape for all x values, right? In other words, it's parallel to the x-axis, right? So let's see what we got there. Notice if z is 0, y would have to be 2. Right? And z is 0 right here, and y would have to be 2. So that's a point that lives on that plane. Right? Then if y is 0, z is 2. So 1, that's up here. 2. Okay. All right. So I have a plane that's now going to try to cut this paper towel ring, right? I always think of cylinders there as like, the center of a paper towel, right? Paper towel thing, right? And I try to visualize as much as I can. What if I chopped it like this way? What would the shape of that be? I try to ground this visualization in like objects that feel, touch, can see, right? Can manipulate like this, right? And so that's where I think you get the more practical use of this. It's like, okay. And that's how you improve your visualization, right? You actually have to almost make it, right? Yeah. I mean, you guys have like 3D printers and stuff. We didn't have that. I mean, I could imagine myself going to a 3D printer and printing a lot of these things just to see what this looks like, right? But we have so many tools that we just didn't have back in the day. But anyway, who cares about that? So here's what I want to do, right? So I'm going to just draw this lightly because I do want to just chop the paper towel roll here with this plane like this, right? So what if I took this tube and I just cut it like shoom, at that angle? Do you see that? That's a plane, and I'm just going to cut it like that, right? What that ends up doing, it looks like, should be something like, I don't know, like that, right? I regret drawing this so far out there. This should be more like this. And then once you're a little bit more sure about your lines, you can start to darken them. That's a helpful thing I found. Like that. Right? So yeah, so this is not needed anymore. None of this is needed anymore. I'm now just focusing in on this shape, right? And don't darken this one so much. I sort of have ruined the perspective a little bit on it because I've really darkened that. So it looks like this is like sticking up, or maybe this is coming out in front. It's not. It should be behind, right? So this should be lighter. So I don't know. To do that, maybe make this darker. I don't know. I am not an artist, that's for sure. Okay, I think that's good right there. All right. So that's what we got going on. Now let's integrate. Think about your shape, right? If you want to do a DZ first, do you see that I would have to go from the bottom of the tube to the top of the tube, vertical arrows, right? And I really don't want to do that if you think about it, because the bottom of the tube is, well, z squared equals 1 minus x squared. That would be z equals plus or minus the square root of 1 minus x squared. The bottom of the tube, the circular bottom, right, is z equals minus root 1 minus x squared. And the top would be z equals plus square root 1 minus x squared. I don't think this would be appropriate geometry-wise or helpful to do dz first. I don't think that's going to be helpful. It's not helpful to think of this as bottom of the tube to top of the tube. Right? We have a similar issue with dx. If I thought about it from back surface to the front surface, that would be like, the back of the paper towel tube going to the front of the paper towel tube, like that. That would be problematic because that would be x equals plus or minus the square root of 1 minus z squared. Neither one of those options looks great. However, dy looks awesome, right? Because if I do dy, arrows start on the left wall and then they go out until they hit this right wall. And it sort of doesn't even see the circularity. It just starts from this wall, which is y equals 0, until the arrows go out and hits this wall, which, what is this wall? Why does this wall exist? That's the wall we got from this plane, which is this formula. See that? So doing a dy first makes a lot of sense, and we have the formulas here that sort of make that the great choice. Let's do that. So if I say the triple integral, square root of x squared plus z squared. By the way, that also makes the integration nice here. Notice how there's no y in this. And so that will make that integration actually easier as well. So there's multiple reasons to choose different orders. Usually it's because the geometry, or it's because of what you're integrating. Sometimes it's both. So let's do dy first. Then we'll figure out dx dz later. So y starts at the left wall, which is y equals 0. And it goes to the right until it hits this wall, which is the plane, y equals 2 minus z. 2 minus z. Now, second picture time. What does this look like if I were to look at it down the tube like this? What would it look like in the xz plane? Okay. Well, luckily, I mean, we've all looked at the paper towel tube, right? Down its edge, it looks like a circle. All right, and so indeed it does. This would be looking down the tube. Right there. And this is, of course, x squared plus z squared equals 1, right? So you now have a choice, right? I could choose to go from bottom to top, like that. So I could finish this off by doing dz dx. I could choose this way. This would be dx dz. But neither one of those are great, right? Because it's from half the circle to the other half of the circle. Do you have any suggestions on how I might do this instead? Wouldn't this be awesome to break this down into polar? Because here's what we're actually doing. This is dy dA for now. I haven't made the choice on how to unpack dA. And remember, dA has, two rectangular options. In this case, it has dx dz or dz dx. But there's a third option, isn't there? dA could be written as a polar graph. And that would be amazing because in the polar world, this would just be r equals 1. So I suggest a radical plan. Break this down into dy, r dr d theta. That's the only really appropriate way of doing that. Otherwise, you're going to be going from some negative square root of a thing to a positive square root of a thing, which isn't bad for setup. You can certainly write it down and say, yep, that's the setup. But when it comes to actually calculating that, that's going to be less than ideal, less than ideal. So let's make that decision. I'm going to now choose dA to be r dr d theta. Okay. But remember, this is in the xz plane. So remember, x is r cosine theta, but playing the role of y is z. So that means it's r sine theta. And that also means that x squared plus z squared equals r squared. Those are what the formulas of polar look like in the xz plane. We're so used to doing the xy plane, but now the y has been replaced with z. But the relationships are the same. The relationships are still the same, just the labeling has changed. Awesome. Okay, so let's get to it. I want to now think about what this would look like. Okay. This is going to be from 0 to 2 minus now z. Wait a minute, z is not allowed in polar, is it? And so z equals r sine theta. That would put an r sine theta there. So that made that more complicated, unfortunately. But look at this great simplification we had here. This is the square root of what's x squared plus z squared? That's r squared. And then we have dy. And then a is r dr d theta. So I'll put the r there. And then we have dr d theta. R goes from 0 to 1. Theta goes from 0 radians to 2 pi radians. See that? And one more simplification, and then we will be good with the setup here. These are all the same. I just want to say the square root of r squared is r. R times the r that's there actually gets me an r squared. That would be a setup that I would not mind integrating. I'm not guaranteeing it's easy because this will provide some complexity. But I think you will clearly see that if you try to set this up with a dx dy or dx dz, the negative square root and the positive square root in actual practice is going to be nightmarish. Yeah. All right. How are we doing with this? Hope you're doing okay with that. Okay. Sometimes you have to switch the order. Sometimes you do have to switch the order. You don't really have a choice. So let me look. There was a problem. Now I'm doing a problem out of our book. This is going to be example 3 in our book. Here they set up a triple integral for us, and you should totally be suspicious when they do that. They're like, okay, evaluate the following. The integral from 0 to the square root of pi over 2. I mean, okay, that's weird. Of the integral from x to the square root of pi over 2. What's with the square root of pi over 2? Stop that. Of the integral from 1 to 3. Okay, that seems pretty reasonable. Sine of y squared dz, dy, dx. Okay. All right. Let's see why this might be problematic. The first integration is not going to be problematic at all. In fact, I could almost do it in my head, right? Because it's z. So this is going to be z times sine of y squared from 1 to 3. So I'm going to plug in a 3 minus plug in a 1. So the first integration is almost trivial. It's going to be 2 sine of y squared. But then I have to integrate sine of y squared against y, and that's a problem. That does not have an elementary antiderivative. So it's not the first one that's bad. It's we cannot integrate sine of y squared against y because there is no antiderivative closed form for that. Oops. This means that we need to switch the order to see if the switching order will fix that. In the order presented, this is not good. I cannot integrate the sine of y squared against the y, right? We're just stuck. So if I switch the y with the x, does that help? Does that change this somehow so then I can integrate it? That's usually what happens, right? So since we cannot integrate sine of y squared with respect to y, we switch the order. Okay. Now that's not as easy as it sounds. Oh, it's just like switch the order. Well, I do need to get a hold of what this looks like three-dimensionally and then see what that looks like, right? So I still need to get a visual of what's going on here, right? So good news is if it's dz first, I'm talking about arrows that go from bottom to up, right? Vertical arrows. And it starts from the plane z equals 1. That's pretty easy to visualize. And they go up until the plane z equals 3. So the start is always z equals 1, this flat surface. So it's flat on the bottom and it's flat on the top, right? So that's not bad. So I know that I'm only talking about from z equals 1 to 3. Okay. Now, the rest of this is a dy dx integral. So let's go ahead. I'm going to draw my three-dimensional picture here, but I'm not going to draw that first. I want to take a look at what this looks like in the projection of y in the xy plane. So let's do that. So here's the x and the y axes right there. Now, remember dy dx is vertical arrows in the xy plane. So this starts at y equals x. Okay, y equals x is a diagonal line. Like that. Right? It starts at the bottom there, and it goes up until it hits y equals this constant. I mean, it's a weird constant, but it is a constant, and it's the square root of pi over 2, whatever the value is of that. So let's say that that is this. So I start at y equals x, and then it goes up until it hits square root of pi over 2. Okay? And then it does this for x values between 0, right, to square root of pi over 2. So we get this triangular shape like that. That's what this thing looks like from a top view, right? So what does that mean for over here? Well, so that means that if I do something like this, oh, see, I'm not using as soon as I don't use my ruler, right? This is square root of pi over 2, let's say. This is square root of pi over 2 over here. And we go 1, 2, 3. And so this does this sort of triangular shape like that. This way, out back here, until it goes like that, like that, like that. Something like that. Now, this I did in GeoGebra. So I did type this in GeoGebra. Now look at all this garbage over here that I had to do to get this thing to even look like this. But the payoff is that I can move this around. See that? I can move this around. So that's worth it. Right? But this took me a while to sort of construct this picture, right? Now, let's confirm what I mean by looking like above, right? So if I choose to do a DZ integration first, which I still think we should do, right, is that I need to go from bottom surface to top surface and then look at it from above in the XY plane, like that, right? Okay. If I chose to do dy first, well, now that's going to go from the left wall over here, starting at that left wall and going out towards this right wall, this rectangular face right here. And then I would have to look at the projection in the XZ plane, which isn't bad. That would just be a rectangle in the XZ plane. So that shouldn't be too difficult either. So I could totally do Y first here if I wanted to. Except, remember why we didn't want to do Y at all? Because if I do Y first, now I have to integrate sine of Y squared against Y. So geometrically, this was fine to do dy first, but because I can't get through the integral of that, it's not really an option, is it? So this really brings into light that there's two sources of difficulty for integration, isn't there? There's the geometry of the region. It's this that could provide difficulties, but it's also what I'm integrating inside of here that could provide difficulties. And so accommodating both of those sources of difficulty can be quite difficult, right? Can be challenging, right? So even though this would be okay to do geometrically Y first, we're stuck right away instead of just being stuck secondly. So I'd really want Y to be last. That's what I really want to have happen. That gives me the most chance that this will change along the way and I'll actually be able to calculate it. So let's take a look at what dx would be visually. If I did dx first, now I'm thinking back wall, which is this rectangle here, that back wall going to the front, and then looking at the YZ plane, like that. And that doesn't look too hard at all either. And so the geometry is not the issue here. The geometry is not the difficulty. It's literally just the integration itself that is the problem there, right? Okay, let's get to paper, and here we go. So I am going to stick with dz first, and then just see if I can swap the dx and the dy. Let's see if that works. So my second attempt at this integral is going to be sine of y squared dz from 1 to 3, but then let's do dx dy. Now that means when I look here, I'm going to do left to right arrows, that, because it's dx dy. And so this starts at x equals 0, that vertical line, until it hits this diagonal, which is x equals y. And then y goes from 0 up to square root of pi over 2. And now let's see if we can actually attempt this integral. Like I said, the first integral is going to be easy. It's integrating this with respect to z. Okay. So I get the integral of that. So I get 3 minus 1. So that's going to be 2 sine of y squared. But now with respect to x, so you're saying there's a chance. Okay, I can factor the 2 all the way out if I need to. And now I can integrate this with respect to x. That's going to be x times sine of y squared from 0 to y. dy left over. And look what happened. Now a y will sit here. That does change the function and renews hope of being able to integrate this. Plug in the y minus plug in the 0. And so now I'm looking at this integral. This is a u sub. We could just let u equal y squared, then du is 2y dy. So 1/2 comes out, cancels with the 2, So 2 divided by 2 is 1. Y dy gets sucked up in the du. This is sine of u. The integral of sine of u is negative cosine. So I'm going to get negative cosine of y squared, evaluated from 0 to the square root of pi over 2. And now all of a sudden the square root of pi over 2 makes a lot of sense. Just check out what's going to happen here. I'm going to plug this in. I get negative cosine of pi over 2 minus a minus cosine of 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. This silly thing is 1. The triple integral of that is 1. Interesting. Okay. I think that's a good place to stop for today. We get another crack at this on Thursday, where I'll introduce a little bit more. We'll talk a little bit more about other coordinate systems, right? In fact, pro tip, we already did cylindrical. Remember when I did the polar instead? That's cylindrical, and that's the next section. But it didn't feel like cylindrical. It just felt like the, reasonable thing to do when I had a circular region, right? And that's all that using cylindrical is, right? But next time we will also talk about spherical coordinates and how to set up triple integrals in spherical coordinates. That's a little bit more dicey, but we will do that and tackle that next time. So looking forward to that next time, by the way. Hope you're taking care of yourself and each other. And until next time, be well, everyone. Bye now.